Okay, hello everyone. Welcome to another Learner Chair session. Today we have Tianyu Zheng with us. He's gonna present his latest work on KiloNova. KiloNova is basically a non-uniform PCD system with zero-knowledge properties derived from genetic folding schemes. In particular, it has been inspired by the work of Kothpali et al. In HyperNova. And what Tianyu is going to present us today amongst his work is how it specifically KiloNova ensures that we have zero-knowledge properties satisfied within our folding scheme proposal. So thank you very much for coming today, Tianyu, and the floor is yours. You can start whenever you want.
Okay, thank you for the host. Hello everyone. It is a great honor to be here to share you with our recent work, KiloNova. And the authors of this paper included me and Dr. Shanggao, Dr. Yu Guo, and Dr. Bing Xiao. And this paper is now published on the ePrint, so you can check it there. Okay. Today I will present my work mainly in 5 parts. Okay, the first part, let's begin with the first part of the background. So in recent years, there is an exciting breakthrough on the research of recursive snark. And this scheme is also called the folding scheme or the accumulation schemes. We use them interchangeably. And a large number of papers are published since the 2019 when the first scheme called Halo is proposed. Here, okay, the Halo. And based on the Halo, Boons and the other authors further summarize a theoretical model for the construction of Halo and propose the concept of the accumulation scheme in 2020. And here's the paper BCMS 20. So before Halo, people build recursive snarks by directly checking the proof in the recursive circuit. So this construction has very low efficiency because the non-native operations is very expensive. For example, we need to implement the pairing or the scalar multiplications in the recursive circuit. And Halo introduces us an idea of folding and deferring these costly verifications to the end of the computations. So at each recursive step, it only checks the validity of the folding scheme instead of the proof. Okay, and another work I want to highlight here is the Nova. Nova published in 2022. So from the perspective of the serious work of Halo, Nova seems to be a very aggressive idea. So in Nova, not only the proof, it it almost differs everything in a NARC. Okay, so specifically, it directly folds the committed R1CS instances instead of the proof. So therefore, their recursive circuit is extremely small and resulting in a better performance. So the following work of Nova we listed mainly focus on adding some appealing features for the IVC or the PCD. So for example, the supernova try to achieve non-uniform circuits and the work like hypernova and the protostar and the protogalaxy try to use more expressive constraints than R1CS, for example, the Planck. Okay, so usually this work aims to build a primitive called the incrementally verifiable computation, okay, abbreviated as IVC. So they build IVC from this folding scheme and claim that this IVC is as their main contribution. So some other work further proposes a more generalized one called the PCD, the proof carrying data. Okay, these two primitives have many important applications in our real world, such as the zk rollup and building virtual machines and so on. Okay, next, let me further explain more concretely on these two primitives. Okay, first, the incrementally verifiable computation. IVC enables us to producing the proof of a statement that long-running sequential computations, as we depicted in the first figure, okay, the IVC produce the proof that this computation is correctly executed. Okay, so this is the statement and the main purpose of IVC. So we can see in the figure here, I put here that an incremental computation, it actually includes multiple steps. And for each step, for the n step and the number n step as an example, in this step, it take the input of a value. Here is Zn minus 1, and we'll have an output as Zn. And it will also take an input, a secret input as the Wn. Okay, it's optional. So for this single step in IVC, the prover needs to compute the above computation. We denote it as the function f. So this f function will take Zn minus 1, Wn as the input, and output a value as Zn. So in the IVC, the prover computes this step by step, so on and so forth. And so theoretically, it can be infinite computations, and we can stop just at anywhere, for example, at here, and produce a proof that shows that the previous two steps has been executed correctly. So this is the function of the IVC. Okay, so you can see here IVC is actually a simple sequential computation. Okay, it's just like a chain. So what is PCD? The proof carrying data is it actually generalizes the simple structure of IVC into directed acyclic graphs. So in the graph, each node may have multiple inputs and multiple outputs. For example, the number n node we depicted here, it will have multiple inputs, and it will also have multiple outputs. Okay, so I just draw one here. So in the definition of PCD, we don't use a function f, but alternatively, this definition gives a predicate denoted as phi here. And this predicate will output a bit of 0 or 1. Here 1 denotes that at this step the prover has correctly compute this computation. So actually the f function in the IVC can also be represented by the predicate. Okay, so another difference I want to highlight here is in the PCD, we usually will consider a situation that multi-parties will participate in the computation. Here, each node may not denote as a step. It may also denote that a particular party who participate in the system. So here, for example, the first node may run by user A, and the second node may run by user B, and they are mutually untrusted parties. So while in the IVC we usually consider there is just one prover who will continue the computation of this series of functions. So in PCD we are more tend to consider a multi-party situation, and this situation may raise some privacy concerns we will mention later. Okay, so in a word, a PCD is more complex with a wider range of applications, but relatively designing a PCD is harder than designing an IVC. Okay, so here I try to summarize our research topic. Okay, so current research on IVC or PCD are mainly based on the folding schemes. Okay, we can divide them as two directions. The first here is we aim to build IVC or PCD with better performance. So basically, we can measure the performance of a PCD in 3 dimensions. Okay, the first dimension is the prover's native cost. And the second is recursion overhead. Okay, these two measurement is actually all executed by the prover, but differently. In the recursive snark, the prover will do some operations locally, but he will also do some operations in the recursive circuit and produce a proof for this recursive circuit and send it to the next step. So owing to this reason, we separate these two parts and regard them as two measurements. So if we consider for the IVC and PCD, we consider their function f or the predicate phi as they can be arbitrary computations. So the main fact that will affect the whole performance of our system is dominated by the folding scheme. So here, for the prover's native cost, it is mainly dependent on the folding scheme prover cost. Okay. And for the recursion overhead, it is mainly depends on the folding scheme verifier cost. Okay. And another measurement I want to mention is the decider cost. Okay, the decider. Okay, decider is actually a denotation used in some PCD papers. So in IVC we don't use decider, but actually they are the same things. For example, in an IVC, if the prover wants to run a series of computation, and after after finishing this computation, he needs to provide a proof path to so-called the IVC verifier. Okay. So in PCD, we call this IVC verifier or the PCD verifier as the decider. Okay, so the decider cost is also matters. Okay. Okay, so this is the first research direction for IVC and PCD. The second we are interested at is to add our current IVC or PCD with more appealing features in our real-world implementations. Okay, so in general, these features can be summarized as this four. Okay, the first is to implement PCD with more expressive constraints. As we mentioned above, so for Nova, it is based on the R1CS relations. But R1CS relations is a quadratic relation. It does not support the high degree constraints nor the lookup argument. So in the following work, such as HyperNova, it tried to replace R1CS with more expressive constraints, also called CCS. We will introduce it later. Okay, the second feature we are interested in is called the multifolding. So actually, in the previous slide, I have introduced the PCD, the construction of PCD. So you can see that the PCD requires a multifolding as a default option, right? Because in a DAG graph, this graph, each node will take input of multiple instances. So to build a PCD, we need to first build a multifolding schemes. Okay, but IVC does not need a multifolding scheme. But as mentioned in Product Galaxy, I remember the authors also argues that the multifolding scheme, implementing a multifolding scheme is also meaningful in the IVC system. Okay, this is because we can use this multifolding to scale the performance of our system. Okay, the third feature is the non-uniform circuits. Okay, this is a very popular features because if we try to implement a virtual machine such as the ZK or RISC-V, we have to uh, achieve this property because those virtual machines may have a rich instruction sets. Okay, the last feature I want to mention is the zero knowledge. So as we mentioned in PCD, since the PCD needs to consider the situation that multi-party, the mutually untrusted multi-party, will participate in our system. So to provide the privacy, we need to add the zero knowledge property. We need to provide this privacy preserving techniques for our users. Okay, so for generality of our discussion, we will mainly focus on the design of PCD instead of IVC because we need to include the multifolding property here. But also the IVC is a specific example of PCD. So our work, if we can present a construction for PCD, we can also present apply this construction to the to IVC. Okay. So in summary, we upon these research topics, we developed our motivations in two folds. The first is the question that can we build an efficient, non-uniform, non-uniform multi-folding schemes for those high degree constraints. Okay. This this includes the features we mentioned, the first feature, and second and the third. And if we can realize the first, then we can further construct a zero knowledge PCD from this folding scheme we proposed. Okay, so here we try to achieve the fourth features as zero knowledge for our PCD. Okay. So we got our motivations, but there is some realistic challenges that we may encounter in our implementations. So let me introduce them to you. So when we try to construct a PCD system, we may faces various of challenges. Okay, the first problem is that although we got a lot of very efficient folding scheme or accumulation schemes in recent years, but after our investigation, we found that most of these folding schemes are incompatible with PCD. Okay, one main reason for this problem is that those multi-folding will introduce cross terms, especially for those high degree constraints. Okay, let me show you a case for this problem. Okay, uh, as shown here, if we try to fold two, sorry, there's a typo. If we try to fold two quadratic relations. So what is a quadratic relation? For example, we got an input as x1, and we compute the square of x1, and to check it whether it equals to y1. Okay, similarly, we got another instance with the input of x2, and also the square of x2 should equal to the result of y2. So usually, if we try to fold these two instances, we could prefer to use a linear combination. For example, we can compute a new folded input as x prime. It equals to the first input x1 plus c time a random c times the second input x2, and then we need to compute the square of this folded input. But unfortunately, if we directly do this, we will find that the square of the folded instance does not produce the same folded result as we expected. So you can see on the right hand side here, if we directly fold the result y1 and to the result of y2, this equation will not hold. So to make this equation hold, previous papers introduced some techniques to send some extra cross terms. Okay, these cross terms are additional costs that we need to pay in the folding scheme. So here for the quadratic relation, to make the equation hold, we need to send an extra cross term as x1 times x2, right? This is our cross term. And the verifier need to add this additional cross term and times c, also times to the right hand side to make the equation hold. So in some low degree relations, for example, the R1CS is only include quadratic relations. So we need only to send several cross terms. It does not seem to be a very severe problem. But if we take the high degree constraints into consideration, for example, if we try to fold multiple instances, okay, totally in S instances, and for each instance, it contains a relation of the highest degree of D. Then how many cross terms we have to send? Okay, according to a previous paper, that we need to send a very, very large number of the cross-term, which is dependent on the d to the power of s. So this actually is a very severe problem that it will make the obtained system as totally impractical in the real world, right? So this is the first challenge we encountered when we try to construct a PCD for especially for from those folding schemes. And the second and the third challenges is about the appealing features we mentioned. The first is the non-uniform, and the second is zero knowledge. So they all encounter the similar problems in the first case. Okay, let's first see the case 2. So if we try to achieve the non-uniform property, it means that not only the input, the circuit input x1 and x2 here, they are different, but and also the circuit itself, their constraints. For in RSS we write them in the matrices. So these matrices are also different, right? So in previous scheme, we only consider that we fold a times x1 and a times x2. So and equal to y1 and y2. Since each of these equation is linear of the input x1 and x2, so we can directly fold them together and there is no cross term. But if we consider the non-uniform circuit, then our equation will become actually the degree is increasing, right? So for this, since the A1 and X1 they can all be regarded as the variables. Okay, so this constraint has two variables, and this constraint has two variables, and their degree is actually 2. Their total degree is 2. Right. So if we use a linear combination to fold these two equations, there will be cross terms. So actually, these problems also hinder us to build a non-uniform folding schemes and further a non-uniform PCB. And the third problem is about the zero knowledge. Okay, we illustrate this problem in case 3. So again, we consider a quadratic relation as we mentioned in case 1. For example, the x1, the square of x1 equals to y1. So if we try to provide zero knowledge for our folding scheme, what's the common method we use? Okay, it's masking value, right? To here the x1 may contain some private information. We also denote as the witness, right? The witness W. So if the prover do not want to leak the information of the witness, he has to sample another random vector that with the same length of the witness, W, and mask the witness W with this random sampled vector. Okay, and also add a challenge C as a weight. Here the random sampled vector is denoted as WR. So let's look at this form of the masked witness. So actually it is another linear combination, right? So if we put this linear combination of W into the quadratic relation, okay, we compute the square of this masked witness, then what will happen? We will gain another cross term, right? So in summary, when we try to construct a PCD system, we have to solve these challenges to make our system truly practical in the real world. So upon the above problems, I summarize our contributions as follows. So in general, our paper can be divided into three parts. The first part is called the relaxed CCS relations. So typically, there are two paths to solve cross-term problem. Okay, the first is that a series of papers from Protostar and Protogalaxy, they try to reduce the number of the cross terms after they already generated in the folding scheme. And they try to use some makeup approaches such as the Lagrange basis and to try to aggregate this cross term up and so that they reduce their number. And the second path is to first transform our relation into a linear forms. Okay, since our relation becomes linear forms, if we directly fold them up, there will be no cross terms. And through this path, we can totally avoid this problem. So in this paper, we choose the second path, okay, following the idea of HyperNova. So to design a relaxed CCS relations, our first step is to build an early stopping version of the super Spartan. Okay, and then the super Spartan will yield some linear claims, and we call them the relaxed CCS relations. Okay, those relaxed CCS relation only contains the linear constraints on both the circuit structures and the instance witness pair. Okay, this is essentially here is the matrix we mentioned in our example, the matrix A, A1 and A2, and the instance witness pair is essentially the vector Z we mentioned in our example. Okay, so with these relaxed CCS relations, we can further build a folding scheme based on it. And so the next part of our paper introduces a non-uniform multi-folding schemes from those CCS relations. And also, the folding scheme does not have cross terms. And also, our folding scheme is very efficient, and its performance is comparable with a cutting-edge work HyperNova, published in 2023. Okay, so now actually the first two parts solve the first question that we obtain a non-uniform multi-folding scheme, and it is very efficient. So our final goal is to build a zero-knowledge PCD from this folding scheme. So in the final part of our paper, we introduce a new construction for zero-knowledge PCD. Okay, to achieve this, we need to first transform the generic folding scheme into a ZK version. Okay, and from the ZK folding scheme, we can build a ZK PCD. So actually, there is some technical gap between this statement. So the second subtask we made here is to propose a new theoretical model for the construction of our ZK PCD. Okay, and it can be regarded as a theoretical contribution of our paper. So, and the third point is that we also consider some potential problems that we will meet in our building for the PCD. Okay, in the real world implementations. So against this efficiency problem, we further propose an optimization technique called the PCD delegation. Okay, so this PCD delegation can enhance the performance of our whole system. Okay, so far, do you have any questions about the first part?
There's nothing in the chat, so it seems that for now everything is clear.
Okay. So if there is no question, let's move on to the second part, the relaxed CCS relations. Okay. To introduce our relaxed CCS relations, we need to first give a quick recap of the Spartan and the super Spartan protocol. Okay, so generally, a Spartan is a polynomial interactive oracle proof, the PIOP, for the R1CS relations. Okay, it is proposed in 2020. Okay, and it has some good properties such as the fast approval and uh, uh, and other things. Okay, so for the Spartan, we generalize the whole process of a Spartan protocol and into three main steps. The first step we called it as encoding. Okay, this encoding actually help us to transform the R1CS relations into the polynomial forms relations. Okay, why we need to do this is this is because we want to use the sum check protocol to prove these relations. So we have to make our instance into polynomial form, okay, which is compatible for sum check protocol. Okay, so upon this polynomial, we need to execute 2 rounds of sum check protocols. This is because in the R1CS relation, as we mentioned, there are some matrices, okay, A, B, and C, and this matrices actually has 2 dimensions. So we need to encode these 2-dimension matrices with a multivariate polynomial, and this polynomial have 2 dimensions of variables. For example, the polynomial is denoted as f, and it has 2 dimensions variables as the vector x and the vector y. So our remaining task is to separately or iteratively to run the sum check protocol on each dimension of our variables. So the second step is to run sum check protocol on vector x, and the third step is run sum check protocol on vector y. So to explain our problem clearly, we need to further dive into the concrete step of this each part. Okay. So first, let me introduce the first part. Okay, in the first part, we need the prover need to encode the R1CS to polynomial. So upon this problem, the first thing he needs to have is R1CS relation, right? And the R1CS relation includes mainly 4 elements. There are 3 matrices, A and B and C, and also a vector Z denotes as the instance witness pair. So the R1CS relations is an equation that contains the computation of these four elements. And here, the circle denotes the Hadamard product, also denoted as the entry-wise product. And after the computation of these elements, and the right hand side yields a zero vector. A zero vector here denoted here. So Our main purpose is to transform or encode this relation into a multivariate polynomial form. So how to do that? Okay, let's take the matrix A as an example. So here is the matrix A, and it is of the size of m times n. Okay, so to transform it into a polynomial, what we do is to use two dimensions of vectors, the vector, sorry, the vector x and the vector y, to separately encode the row and encode the column. Okay, actually they encode the index of the row and the index of the column. So take an example. Those vectors, these vectors are actually binary vectors. So if the vector x equals to 0 everywhere, okay, it is a 0 vector, and vector y equals to 0 everywhere, okay. This means that we select the first row and the first column element in the matrix, right? Actually, we select this matrix, this element, and this element uh, is actually the evaluation of the polynomial. So here is the f is evaluated on x and y, and x and y equal to 0 vectors. Actually, it will equal to the element of the first element of the matrix as a11. Okay, or a00. It is more useful. Okay. So with this technique, we can write the matrix into the polynomial. So we can derive this form into the very complicated equation, the expression below. But actually, it is very easy to understand it. So if we look at the first sum here, okay, what does it mean? Okay, as I already told, the matrix A is encoded as a polynomial on the variables of vector x and vector y. So similarly, we can also encode this vector z, the vector z, with just one dimension of the vector y. Okay, so the polynomial z has the one-dimension variables as vector y. So what does this sum on the vector y means? Okay, so we back to our example here. Here is the matrix A we use, and according to the R1CS relation, we have to multiply the matrix A with the vector z, right? So if we specified an index x, for example, we specified uh, the second index of the y, then we actually pick the second row of the matrix, right? And in the multiplication, this second row is multiplied with this vector z. Okay, and actually we are compute an inner product between the second row and the matrix and the vector z. So how to express this inner product? Okay, since in inner product we multiply each element in the vector one by one. We multiply the first element to the first element of Z, and the second element to the second element, right? So we actually can use the vector Y as a selector to select this element. For each value of Y, we select one element in the vector. Since we need to compute the inner product, we need to select every element in the vector. So here, this inner product computation can be write as a sum, actually a sum on the field of the y of the vector y. Okay, so similarly with this transformation, we transform the a times z into the first part of this expression, and the b to z to the second part, c to z to the third part, right? And we also computate them with the corresponding coefficient. So, but there is one more question. Since we transform this, we will obtain multiple inner product results, right? Here in the R1CS relation, the right-hand side is actually a vector of 0. Okay, so we will got here the vector, the length of the 0 vector is n, I think. Is m. Okay. So we will got m constraints in the polynomial forms. So, but our goal is to build a polynomial for the sum check. So we have to aggregate this m constraints into one constraint. To achieve this, the previous task actually introduced another equivalent functions and multiply it to the polynomial instance. So this equivalent function actually it will output one only when his two inputs, here the vector alpha and the vector x, they are equal. If they are equal, this function will output 1. And in other cases, it will only output 0. So we won't talk too much about these operations because it's unrelated to our discussion. So here I just write it here, and it is meaning for the aggregation of the 0 vector. Okay, to the 0 bit. So so far I have introduced the first part of the Spartan, and we use encoding to encode the R1CS to the multivariate polynomial. Okay, so next what we're gonna do, the second part of the Spartan is to run a sum check on this polynomial we obtained. Here we first obtain a polynomial of x, and the prover claims that if the sum of the polynomial f equals to 0, then we can obtain that the R1CS relation is holds, right? So the verified task is to check whether the prover tells the truth. Okay, so the verifier needs to check whether this sum holds. So what he used is a sum check protocol. So I don't talk about the details of sum check protocols. Okay, so generally speaking, this sum check protocols takes log n rounds interactions, and to check this sum claim, this claim on the sum, right? So in this log n interactions, each interaction, the verifier needs to send a challenge to the prover. So in total, there are log n challenges, and this challenge forms a challenge vector. We denote it as the vector Rx. Okay, and as the final step, the prover needs to present an evaluation of the polynomial f on the challenge vector or vector Rx. Okay. So in the right side, the prover sends this claim to the verifier, and it claims that the polynomial f evaluates on the vector Rx equals to the result to a value cx. Okay. Okay, so this claim, okay, for this claim, the verifier doesn't believe the prover, so he needs to further to check whether this final claim is correct, right? So to do this, the verifier can further reduce this claim to several subclaims. Okay, as we presented here. Okay, so this part is actually we mentioned before the inner product, right? The inner product. So to check the previous claim, the verifier asks the prover to separate to reduce this claim and send again these three subclaims, and these subclaims each contains a result as sigma m. Okay, the m uh, can be a matrix as matrix A, matrix B, or matrix C. So in total, the prover will send three claims with the claimed value as sigma A, sigma B, and sigma C to the verifier. So what we need this reduction. Actually, this reduction gives us a new instance, and this new instance is also a sum check instance, right? So before, this is an evaluation of f, and the verifier don't know how to do it. So after the reduction, this evaluation becomes three claims on the sum. So now the verifier knows, oh, I can use another sum check on these subclaims, right? And this sum check is run on the vector y. So here I present our the third part of the Spartan. Okay, the verifier will run the second sum check protocol on those claims, and this sum check protocol will produce another polynomial g. Okay, so here one thing I forgot to mention is that although we got three claims here, actually the prover and the verifier can aggregate them into one, and this yields a new claim about polynomial g. Okay, the sum of polynomial g equals to a value sigma. Okay. So in the second sum check protocol, after log n rounds of interactions, the prover at the final step will send an evaluation, a claim of the evaluation about G. So again, the verifier runs the same reduction process, and he can reduce this evaluation into another four sum claims. Okay. This four sum claims contains three claims on the matrices, the matrix A, B, and C, and their claimed value as theta, and another new claim of the vector Z. Okay, this evaluation of Z actually equals to epsilon. Okay, Here the M actually takes input as Rx and Ry. Okay, and evaluates on theta M. So this is the general process of Spartan. Okay, but as we talked, Spartan is mainly built for the R1CS instance, the R1CS relation. But the R1CS relation is not expressive enough. So here is a new protocol called the Super Spartan. It is a PIOP for the CCS relations. And so the CCS relation means the customizable constraint system, and which can simultaneously generalize the current relations such as the Plonkish, the R1CS, and the air. The air is the constraint system used in stock. Okay, so as we know, the CCS relation is actually a very expressive relation. So what does it exactly look like? Okay, so I present the polynomial form here for the CCS relation. Uh, but I think it will be simpler if we compare it directly with the R1CS. Okay, so let me further introduce on the below. Okay, so the CCS in the CCS relation, actually we got a set of matrices. Okay, for example, we got a matrix set included elements of M1, M2, dot dot dot, and till MT. Okay. And this is the set that include all the matrices we will use. And besides, we also need to need some selectors as S1, S2, SQ, SQ. So what does the selector do is that it contains the index of the matrices, and if we according to the selector, for example, according to S1, it will select some matrices for us. For example, the S1 may select the matrix M1 and M2, and then according to the matrices selected, uh, we can compute a product according to the matrices. A product. Okay. And the product may include the M1, M2, and the vector Z. Okay. And finally, each selector will produce a product. And to construct a CCS relation, we sum this product together. And for each product, we add another coefficient as CCI, C1, C2, CQ. Yeah. And we sum them up. So it is also abstract, right? But we can compare it with R1CS, it will be clearer. So in the R1CS relation, we also have a matrix set. This set includes the matrix, three matrices, A, B, and C. And to build an R1CS relation, we have two selectors, S1 and S2. Here, the S1 selector will select A and B and produce a product as AZ Hardeman product to BZ. Okay, this is a product. And for the selector S2, it will only select one matrix as C and produce a product only contains C times Z. And finally, we add this product into one. And for each product, we also attach a coefficient For the first product, we attach a positive one, and for the second product, we attach a negative one. Okay, and this sum will finally equals to a zero vector. So this is actually take the R1CS as a specific example as the CCS relations, right? Okay. So the CCS relation I write here is actually an encoded relation. It is not in the vector form. It is in the polynomial form, but it is quite similar to the R1CS relation we mentioned. Okay. So you can regard this Mj as A or B or C here. So it is more clear. And you do not need to remember this relation because we only consider we will only focus on the results produced in the super Spartan. Okay. So what super Spartan do is actually replace the R1CS relations in the Spartan with the new relations as CCS. So similarly, the super Spartan first runs an encoding, and the second it runs a sum check protocol on the vector x, and third it run another sum check protocol on the vector y. Okay, because the whole process is too complex, so I did not present here, and we only need to focus on those two claims here. Okay, similarly, as we mentioned, the sum check protocol will take an input as a multivariate polynomial. Here we write it again as the polynomial f tilde f. Okay, and the prover and the verifier run a sum check protocol to check that whether the sum of f on x equals to zero. Okay, so after running this first sum check protocol on vector x, the prover will present several claims to the verifier. Okay, those subclaims that we already reduced them. Right? Okay, so after the first sum check protocol, it presents us with the first class of claims. Okay, those claims are mainly about another sum check protocol problem, right? It's a problem. It's a sum check on the vector y, and the polynomial includes the matrix polynomial, the Mj, and the vector z polynomial. And the prover claims that the sum of this polynomial equals to a value as sigma j. Okay, since there are t matrices in total, so the prover actually sends the verifier t claims, and each claim contains the value sigma j, sigma 1 to sigma t. Okay. So upon this subclaims, okay, it actually brings a new sum check problem for the verifier. So the prover and the verifier, again, they repeatedly to run the second sum check problem. And on this time, they run the protocol on the vector y to check that whether the first claims are correct. Okay, so after the second sum check protocol, the verifier will obtain a class of new claims. So this time, this claims contains the evaluation of the matrix polynomial Mj and t claims in total, right? And another claim, this claim contains the evaluation on the vector z, and the claimed value we denoted as the epsilon. So this is the general process of the super Spartan. Okay, we explain it with the Spartan for better understanding. So so now we here we only focus on those claims that generated in the super Spartan protocol. So why are we gonna do that? Actually, it it introduces some insights for us about how do we apply our folding scheme for the instances that are generated in the super Spartan. Okay. So now to understand this question, we can take two examples here. The first example is you can try to consider if what if we fold two CCS instances with the same circuit here. Okay, the same circuit means that for each instance, their matrix M1 to MT are the same. The only difference is that the z vector of the first instance is different from the z prime vector of the second instance. So if we wanna to fold those two instances, how do we do? The naive idea is we directly fold them at the beginning of the super Spartan, right? Okay, after the first part of the super Spartan, okay, we already encode them as a multivariate polynomial f, right? So at this position, can we fold them into one? Okay, it is theoretically feasible, but you need to notice that this polynomial f, it has the highest degree of d, right? If we directly fold these two polynomials into one polynomial, then they will generate a large amount of cross terms for us. So how to solve this question? Okay. Is there any question? Okay.
Can start eating.
If no question, hello.
Yeah. Is everything okay? Can you?
Okay. I heard someone's voice, so I think maybe there are some questions. So
No. There's just someone said that they had to go. But you can continue.
Okay. So I just continue. Okay. So I just talk about the question that we want to fold two CCS instances with the same circuit. And the problem is that if we directly fold the encoded polynomial, these two polynomial into one, we will encounter the problem of the larger amount of cross terms, okay? Because this polynomial f has the degree of d. So what's the solution is introduced in HyperNova, that and they also present us an idea that we can continue running the super Spartan right until the right until we finish the first sum check protocol. So what is the advantage of running a round of sum check protocol? So we can focus on the claims here. If we so before the sum check protocol, we got a polynomial of degree of d, and after the sum check protocol, we the prover will present some new claims. Okay, this new claims is only contains the one matrix mj times a vector z, right? So by doing this, the prover and the verifier actually reduce the previous high degree polynomial into some new instances, and these new instances only contains polynomial with the degree of 1. So if we run the super Spartan and stop here, and we regard the new claims as our new CCS instances. Actually, they call this relaxed CCS instances. Then it is feasible for us to directly fold this instance with another instance. Okay, for example, if we directly compute an instance include mj times z, and another instance contains mj times z prime, okay, with a linear combination. Okay, since both of them are linear to the vector of z, so there will be no cross term, right? If we we fold this z vector together, and we only need to compute the z polynomial plus c times the z prime polynomial, and we also multiply them with mj polynomial. Okay, so there will be no extra elements we need to send to keep the original equations holds, because it naturally holds. So this is our first case. We know that we consider two CCS instances with the same circuits. So what if their circuits are different? So here the second case, if we consider the non-uniform situation, and those two CCS instances, they have different vector z here, and also they have different matrices from M1 to MT. And the second instance has M1 prime to MT prime. So in this case, can we still use the HyperNova? So unfortunately, the answer is no, right? Because under this situation, those M and the vector Z, they can both be regarded as the variables of our polynomials. Right? So the total degree of the constraint is 2. And if we try to fold them together, you will find that cross terms will appear. Right? If we fold mj combined with mj prime, and you need to multiply it with another folded z, it's z plus c times z prime. Okay, c times z prime. So this is a quadratic relation, right? So how to solve this question? How to solve this problem? Okay. So again, we can inspired by the HyperNova. The authors introduce another a new round of sum check protocol for the high degree polynomial. and linearize it into a claim. So can we further run another round of sum check protocol? Right. Here we continue running the super Spartan and stop it right until the second sum check protocol on vector y is finished. So with this technique, we will obtain a new claims, and this new claims, as I write here, it contains an evaluation of the matrix M and an evaluation of the vector Z. So what's the point is that the new claims we obtained are totally linear on both the matrix and both the vector Z. Right. So even though we take input as two CCS instances with different circuits, the non-uniform circuits, we won't need to worry about the cross-term problem because we got totally linear claim on each variable, and if we fold them together, there will be no cross-term. So if we fold the first claim and second claim, here mj times plus c times mj prime, right? And the second equation is z plus c times z prime. Okay. So and the right hand side of the equation can also be linear combined, okay? And the equation still holds. So through this technique, we solve the problem, the cross-term problem, and when we try to fold two CCS instances with non-uniform circuits. Okay. As a summary, as I show here, by this technique, we run the super Spartan for each CCS instances and stop the protocol. Right, early stop the protocol just after we finish the second sum check protocol. Right, and so in the original super Spartan protocol, after the second sum check protocol, we need to do another polynomial oracle query, right, to query on this evaluation. So we just stop here, okay. And we do not instantiate these oracles, and the verifier want to query the prover and that. So it's an early stop version. And what we obtain is a relation, is a new relaxed relation. This relation we call the atomic CCS, ACCS. And this new relation contains these elements. So the first line of elements is actually the same to the previous CCS relation. And the second line contains those elements that are generated among the sum check protocols. And we need to also take them as a part of our new CCS relation. So to check this ACCS relation, actually we just compute the claims that we generated here, right here. So the first we compute the evaluation of the matrix M on the vector Rx and Ry, and obtain the result theta j. And also we need to compute the evaluation of the polynomial z and compare it with the result epsilon. Okay. So with this atomic CCS relation, we can directly folding this two claims, right, with another instance, and they will they don't produce any cross terms. Okay, so this is the first part of our paper, and next we introduce how to build a generic folding schemes based on the relaxed CCS relations we introduced. Okay, so based on the ACCS relations, it is seemingly very simple for us to fold CCS instances, right? If we want to fold the input CCS instances, what we need to do is just two steps. First, we run the super Spartan, right? We transform those CCS into our new ACCS, right? We just run an encoding and two subject protocols, and we can obtain ACCS. Now, since ACCS is linear, so we can efficiently fold them up. But here is a problem. Okay, so the first process I introduced only focused on folding the CCS instances, but this is not sufficient for us to building an IVC or a PCD. Why? Okay, let's review the IVC and the PCD structure here. For the IVC, it actually computes a sequential of computations, right? So at each step, to express the function f, we will generate a CCS instance. But what's more is that on the previous step, okay, this is the number I step, and this is I minus 1. On the I minus 1 step, okay, there will be a folding, right? There happens a folding, and this folding will produce a CCS and ACCS instance. The ACCS instance, and this ACCS instance is passed to the next step, and in the next step, the prover needs to fold the CCS instance with the ACCS instance. Right. So actually, I make it more clear is that here is a running instance that is a ACCS instance. This instance is updated every time after the step. There is a CCS, and the CCS is folded in the ACCS. And in the next step, there is a new CCS, and this new CCS is also need to be folded into the running ACCS. Okay, and the ACCS is updated. So here we encounter a situation that we have never considered, right? Since it's before we just consider folding the CCS instance. We do not consider what if we take input of one ACCS and one CCS, right? So the first case we need to consider is that our folding scheme also needs to be able to fold a CCS instance and ACCS instance. So the second case is also important. This only happens in PCD structure, right? So remember that PCD is actually a DAG, right? A graph. And for each node, for each number I node, it will take inputs as multiple instances. And those instances may also contain the already folded instance generated by the previous step. Okay. For example, the I-1 and I-2 step, they separately generated two ACCS instances. And at the I step, the prover needs to fold them together and produce a new one. So this case is also not included in our protocol, right? So we also need to solve the problem that what if we take input as one ACCS and another ACCS? How to fold them together? Okay. So before introduce our solutions about to solving these two cases, we first give a quick overview of the folding of only CCS instances, right? So this process is very similar to the super Spartan we introduced. So at the beginning of the folding scheme, the prover and the verifier will take input as the CCS, okay, multiple CCS instances. And the first step they do is to encoding. They will encode this, okay, the CCS, okay, CCS. This is CCS instance, and encode them into the multivariate polynomial here as the F1 to S1. We assume there is S1 number of instances in total as the input. So after the encoding, we got S1 number of polynomials. Okay. And according to the super Spartan, we need to run some check protocol for each of the polynomial, right? So this means that we need to in total run S1 some check protocols, right? It is too expensive, but thankfully those some check protocol runs in parallel can be aggregated into one some check protocol. So the prover and the verifier, upon this multiple polynomials, they only need to run one round of sum check protocol, and this sum check protocol will produce the first claims we mentioned. And for those first claims, again, the prover and the verifier encode them to the new polynomial G as G. And similarly, they run the second round of sum check on the polynomial G, on those polynomials, right? And they obtain the final claims. Those claims are linear. So we can directly fold them up into only one ACCS instance. Okay, so consider the case we fold the ACCS instances. So what is the problem if we try to fold these instances? Right. The technical gap is that we consider here also in the PCD situation, if the I node takes two instances from another two node, right? Another two node. Since this I-1 node and I-2 node, they are totally independent process that running by maybe different parties, right? So it is nearly impossible that they will use the same challenges for the sum check protocol. Okay, that's the point that we have to solve. For the node I, the instances he takes as input are evaluated on different challenge vectors Rx and Ry. For example, we may got the different matrix polynomial m and m prime, and m is evaluated on Rx1, Ry1 to the value of theta, and m prime is evaluated on Rx2 and Ry2 and obtain the value of theta prime. So if we take these two instances, we cannot fold them into one. Okay, so how to solve this question, this problem? Okay, our solution is that if we have the ability to update this Rx and Ry at the node I here, right? Then we can uniformize this Rx1, Ry1 and Rx2, Ry2 into the same vectors as Rx star and Ry star. Okay. So then we can fold this two instances into one. Right? It makes the things feasible. Okay, so now our task becomes that how to update the challenge vector. So to achieve this, there is already a technique that frequently used in previous work. So what does that technique is about? So we take an example. Now we assume there is a polynomial, a multivariate polynomial that only has one dimension of variables. That is the vector x. We right now we don't consider the vector y here. We only consider the simple case. Okay, and for the verifier, now he has a claim that the polynomial f evaluates on Rx vector equals to a value as v. So now the verifier wants the prover to update this claim. Okay. He wants the prover to update the vector Rx into a new vector Rx prime. Okay. And also the value as a new value v prime. So to do that, the verifier and the prover, they will write a new polynomial as the gx, denoted as gx, and this gx is actually multiply the original polynomial fx with an equivalent function. Okay, and this equivalent function takes one input as the challenge vector, the old challenge vector, and one input as the vector x. So you can see that for the new polynomial gx, it equals to 0, right? It will equals to 0 when the input of the vector x is not equal to Rx. Okay. So these two inputs, if they are not the same, then the gx will evaluate on 0. So the gx evaluates to non-zero only when the inputs are 2Rx, right? This new equivalent function, okay? In such case, this equivalent function is equal to 1, and the gx is equal to frx, frx. So the new polynomial evaluates to non-zero only at 1 point, and it evaluates it vanishes on 0 in any other way. Okay. So now the prover and verifier run a new sum check protocol on this polynomial gx, right? And if they run this sum check protocol to show that to check that whether the sum of gx is equal to the value v. So obviously this claim will hold, because as we deduced before, as we talked about before, the gx only has 1 point of non-zero value. The value is v, right? The value. Okay, so its sum is definitely v. But with this sum check protocol, as we can achieve another target, is that the sum check protocol actually in the interaction, it will use some new challenge vectors, right? We denote the new challenge vector used in the sum check protocol as the vector Rx. So after running of the sum check protocol, the prover sends a new claim about G. And this G evaluates on Rx. And it should equals to a new value of V prime. Okay, so now we got a new claim. This new claim is on a new challenge vector. And moreover, what's more, the polynomial f is contained in the polynomial g, right? So actually, through this technique, we update the challenge vector of f into a new one. Okay, as a conclusion, we got this polynomial g evaluates on Rx prime, and it should equals to a V prime. So so how what is the expression of the polynomial g? And according to the constraint, the polynomial g contains a multiplication between equivalent function eq and another polynomial f, right? And so the eq is public, so the verifier can compute the eq function by himself, and the prover also presents the final claim V prime. So to compute the new evaluation of f, the verifier only needs to move the value of eq to the right hand side. Right? So just let the V prime divide the eq function. Okay, divide the eq function. Then we obtain the updated claim. So by applying this technique iteratively twice, okay, one is for the vector x and one is for the vector y, we can update our ACCS instance with some new challenge vector Rx and Ry. So, and what's more, this process is almost run the same step, the similar process with the folding of the CCS instance, right? Because we apply the technique, we need to run a sum check, and we apply twice for 2 sum checks. And in the folding of the CCS instances, we also need to run 2 sum checks. So, okay, this gives the overview of our folding scheme, right? We only need to care about those main process of this folding scheme. So the right part, the left part is the folding of the CCS instances, right? And it takes some check 1 and some check 2. And for those ACCS instances, we need to run an update protocol, right? This updating protocol updates the challenge vectors. And we also need to run the sum check, the first round of sum check and the second round of sum check. So all those sum check are run in parallel, and we can aggregate them into one process. So in total, no matter how many instances, no matter the CCS instance or the ACCS instances, we take the input in total. We only need to run 2 rounds of sum check. And then after this process, we can fold them up into one instance as the final folded ACCS. Okay. So this is our final scheme. And also note that these instances, we do not require their circuits are the same. So our folded scheme is actually a non-uniform folded scheme. Okay. And we also compare its.
Tianyu? Just
Okay.
yeah, sorry, just one thing. We are over time. It's completely fine. You can continue. Like there's no issues with it. But just to let you know, as I see you are in slide 20 of 36. So just for you to take into account. Of course, there's no issues. Like we can continue. I'm happy to because it's been exciting so far. But just to let you know.
I'm sorry, I'm not clear. So I don't have time, right?
No, you can continue. Like it's not an issue. But from the hour 30 that that this was supposed to last, we are already over time. I was just like pinging you basically. But it's not an issue. We can just continue.
Oh, okay,
Just
okay,
for you
okay.
to
Thank
let
you.
you know.
Okay, I got it. Okay, so I just continue, and there is the last part of our paper. Okay. So I quickly compare the performance of the folding scheme we proposed. Okay, so our folding scheme compared to the HyperNova, we actually have the same asymptotic performance with HyperNova, but concretely, since we stopped the Super Spartan later than the HyperNova, right? So we run another round of some check protocol. So constantly we will take another log n interactions. Okay, if we use the Fiat-Shamir, we need another log n random oracle like hashes. But with this cost, we achieve the features that the HyperNova does not provide. That is the non-uniform circuits folded. Okay. And compared to another paper that recently published just last year, and the Proto Galaxy. Theoretically, the Proto Galaxy has lower recursion overhead because in its folding scheme, they only need the constant size of random oracles. But as I mentioned just before, the Proto Galaxy, they try to solve the cross terms through another idea. Just they try to reduce the number of the cross terms. So to achieve this, they have to apply some other optimization technique, some makeup techniques, and this technique are quite expensive. So the prover cost of the Proto Galaxy is quasi-linear, while our prover cost is linear, right? Because sum check, the prover cost of sum check is linear. So besides, I would also like to mention another optimization that we made for our generic folding scheme. Actually, this is a bonus property that we observed in our design, right? Yeah. So what I try to express here, since we have already run 2 round sum check protocols for our CCS relations and obtain those linear claims, right? We obtain the linear claim on each matrix M1 and to MT, right? So theoretically, these claims are independent of each other. So can we batch those claims, the verification of those claims together, right? This idea is mainly because since in the real world implementation, we have to compute the commitment of this matrix, right? And with some primitives such as based on the DL assumption, right? So if their committed keys are independent, that means that their DL they satisfy the DL independence, right? Then it is secure and totally feasible for us to multiply all these commitments of matrices into one. So now this gives us a very exciting result that our new optimized ACCS instance only contains 2 claims. The first claim is an aggregated matrix, and we need to compute its evaluation. And the other is about the vector z, Okay. So what's the advantage of this optimization? Okay. So the most significant influence of this optimization is that our IVC proof or the PCD proof, okay, does not need to contain those T matrix, right? It only needs to contain one matrix. Okay, so let's move to the final part, is the construction for our zero knowledge PCD. Okay, as we mentioned above, there is actually a technical problem for us to building a zero knowledge folding scheme. Okay, since a ZK PCD requires a basic primitive building block as the ZK folding scheme, right? It needs to build on this primitive. So right now, a common method for the ZK folding scheme is to mask the witness with a random vector. Okay. For example, we just take the vector z as an example. We mask the vector z with another random sampled vector zr. Okay, and with a challenge c. And this linear combination, if we directly put them into the high degree relations, it will bring us the cross terms. The first problem is cross terms. And another another problem is that we need to recompute our relations for this mask witness. So it introduces extra computations for our prover. Okay. Therefore, our main idea is that we try to avoid using the masking value for the zero knowledge property. We try to use some more specific and fine-grained technique to guarantee the privacy of our witness among the process that we run the superstructure. Okay, so To do this, a quick recap of the generic folding scheme we proposed. Okay, this time we only focus on these blocks, and we try to find those blocks that will leak the information of our witness. So, so basically, there are three parts that we need to concern. The first part is the sum check part. Okay, those two rounds of sum check protocols, they actually run the interactions between the prover and the verifier, and the prover will send some response to the verifier. Those response contains the information of our witness. Okay, and the second part is the claim part, right? Those claims, as we mentioned, is actually the evaluation of the polynomial, right? For example, the second claim, it contains the polynomial z, and it contains the evaluation on vector y equals maybe to an epsilon, right? So this value epsilon, it contains the information about the vector z and also the witness. So we have to randomize this value of epsilon. So the third part we mentioned, it actually is not be regarded in the process of the super Spartan. Okay, it's so the third part may leak the information of the witness is the folded ACCS. The folded ACCS. So if we run the folding scheme correctly and with some zero knowledge property, the obtained ACCS will not leak the information of the witness. But we need to notice that after we produce the ACCS, the verifier needs to carry out some polynomial queries to the oracles, right? So in this queries, the queries is upon the folded ACCS, and this queries will inevitably contains the information about the witness, right? So we have to make the folded ACCS itself to be zero knowledge. Okay, we solve this problem in mainly three techniques. The first technique is a technique for providing zero knowledge for claims. And the second is providing zero knowledge for our sum check protocols. And the third is the zero knowledge for our folded instance. So let's talk about the first technique that guarantees the zero knowledge property of the claims. Okay. So as we mentioned, those claims actually, if we directly mask the witness, and it will introduce the cross terms. So our main idea is to how to avoid those cross terms generated among the process. So our idea is from a previous work published in 2020. And this technique is actually already frequently used in the development, right? In the real world implementation. So the general idea is that instead of masking this witness with random bits, we use a padding technique for this witness. So how do we do that? For a vector z, we just pad it with another random vector r here. So in our scheme, we only need a random vector r with length of 2. Okay, I will explain this later. So we just remember that we extend the length of our z with 2 actual random values as R1 and R2. Okay, and correspondingly, to make the equation well-formed, we have to extend the matrix that multiply with Z, right? We also need to extend the matrix to a bigger one, okay? And here we add it with an identity matrix with the size of 2 times 2. And now here we take the R1CS as an example. The R1CS relation becomes in this forms, right? In these forms. Okay, for the CCS, the same situation happens. So for this simple padding technique, there are several facts I want to mention. The first fact is that the padding technique, different from the masking technique, we don't mask this our witness with random bits. We just enlarge them. So with this enlarged space, there will be no cross terms if we try to fold them with another instance. Okay. So for this new R1CS instance, if it is folded to another one, there will be no cross term. So definitely we need to run the super Spartan first, right? And the second fact is that this padding scheme, the number of what we need to pad it, actually it has a regulation, right? So the number we padded must be larger than the queries that we will send to the oracle. Okay, if we queries the oracle 2 times, then 2 extra random values need to be padded. Okay, so that's why we use length of 2, because we in total we got 2 claims, right? And each claim contains a query to the vector z. So to protect the witness among the claims, we need to add extra 2 random values in R. Okay. Okay, this is actually the factor 3. So for the factor 2, that the padding technique that it cannot be used in any cases that we encountered. So it has some limitations. The limitation is that for the query for our oracle, that the query response must be a linear combination that including each element in the witness. Okay, each element in the witness W. But thankfully, the claim that we try to protect, they are all linear combinations of the witness vector. Okay. And the factor 4 actually introduce an optimization. Okay, that's an optimization. Okay, so in the real world implementations, there is no need for us to add random values to the vector z. So why is that? This is because in the implementations, we need already pad our vector that to the length of the exponentiation of 2, right? Because since we got a vector of z, we need to pad it to the length of the 2 to the power of k. Right? So this previous zero padding technique, right, already gives us this place to insert our random values into right. So we can just directly replace some of these 0 bits with our random values. Okay. So actually, this padding technique will add a little cost to the our whole scheme. And the second technique is a zero knowledge technique for the sum check protocol. So actually, it is optional. So let me explain why it is optional first. This is because for the sum check protocols, there are log n rounds of interaction, right? So in each interaction, actually we can regard the verifier as sending a query to the prover, and the prover gives a response back. So, in fact, we can apply the same technique that we used for the claims to the sum check protocols. But what our concern here is that in the previous technique, we only need to add 2 random values. But in the sum check protocol, we got 2 sum check protocol, and in total, we need to add log m plus log n random values to as the padding values, right? So so in case of that, we will encounter the condition that we run out of this zero bits, right? The log m plus log n number is larger than the 0 bits that we have. So under this situation, we have to double the length of our vector. Okay, we need to double 2 to the power of k to 2 to the k plus 1. Right? Actually, it will enlarge our circuit and add extra cost. So for this situation, actually, we provide an alternative technique to provide zero knowledge for some check protocols. Okay, we can also apply an off-the-shelf primitive that is called zero knowledge sum check, given by Chiesa at 2017. So its technique is very simple. We just need to mask the polynomial that we need to prove with another random polynomial of the same size. Okay, and since we mask this polynomial in the sum check protocol instead of the CCS checking the CCS relations, so this technique will not introduce cross terms. And the third technique is the zero knowledge technique for our final folded instance. Okay. And to achieve this is quite simple. We only need to add an extra random sampled ACCS instance to the list of our input instances. Okay. For example, we got k instances to be folded. We only need to add another random sampled ACCS instance, okay, to this k instance, and then we in total fold k plus 1 instances. Okay, and also this zero knowledge technique is very efficient and easy to implement. So finally, through these 3 techniques, we obtain a zero knowledge generic folding schemes at last. So now we can construct our ZK PCD. But there is still a theoretical gap for us when we try to design this scheme. So as mentioned and proposed by BCMS21, Bones has introduced a theorem for the construction of a zero knowledge PCD. So simply, it states that if we try to build a PCD scheme, we can compile any NARC system with an efficient accumulation scheme. So actually, it is interchangeably to the folding scheme. Right? So we can compile any NARC with a folding scheme and obtain a PCD. And if we try to achieve the zero knowledge for our PCD, then there are two necessary conditions. The first is that the NARC is zero knowledge. And the second is that the folding scheme is also zero knowledge. So according to our previous techniques, we only built a zero knowledge accumulation scheme. We didn't uh, uh, we didn't achieve a zero knowledge NARC system. Okay, to further explain this problem, we need to first clarify that what is the NARC mean? What does the NARC mean in the NOVA's construction? Okay, the following figure presents the IVC construction for each step in the NOVA, right? Okay, so briefly speaking, in this step, the yellow box we draw here is the recursive circuit, and the recursive circuit mainly includes two parts of computation. The first part computation is about the function f, that is the function for the IVC, and the second part is the verification algorithm for the folding scheme, right? The fold.v, right? As and to run this IVC step, the prover needs to run the folding scheme prover algorithm, and it will produce a proof pi. Okay, in NOVA, this pi is actually the cross term t, right? And send this pi to the recursive circuit, and the recursive circuit will will check that whether the prover has correctly folded the instances with the pi, right? And output the final folded instance as the big U I plus 1. Okay, below here. So at the same time, the prover in the recursive circuit will execute the function for the IVC, right? And after all these two circuits are finished, then the prover will write the circuits into a new instance here, a new instance witness pair here. Okay. So this instance witness pair is expressed in a CCS relation. Okay, the folded instance here is actually in ACCS instance. So, okay, so what is the NARC for the construction in NOVA? Okay, so actually the NARC specifies the argument system for our recursive circuit. So what does it mean? It means that what the argument system, the prover tries to transform the recursive circuit, okay, into the CCS. Okay, is the NARC. Okay, so for the CCS instance generated, it can be the witness. It can be directly regarded as a proof for the NARC because we don't need to succinct and zero knowledge, right? The witness is actually the proof. And for the verifier of this NARC, it just take the witness and check whether this CCS instance is satisfied. Okay, this is just the verification algorithm for NARC. But the question is that here we only realize the zero knowledge property of our folding scheme. But for the NARC, for the CCS we generated, it is not zero knowledge. But this CCS must be sent to the next step. And if the next step is executed by another party, then the witness will be leaked, right? So then our task becomes very clear, is that we need to guarantee the zero property of the CCS instance generated here. Okay, here is a naive NARC example for the CCS I just mentioned. Okay, the proof for a CCS instance, the prover just sends the witness directly to the verifier, and the verifier takes the witness and checks the CCS relation. Okay. But so our main goal is to achieve the zero knowledge for this CCS, and we need to build a ZK NARC for those CCS relations. But here again, we encounter the same dilemma as we mentioned. If we directly transform this NARC into a zero knowledge version, for example, we use the masking value. This will inevitably introduce cross terms for us, right? Also, if we try to use another, for example, the padding techniques or other things, anyway, we need to instantiate a new process, a totally new process for this ZK proof for the NARC, right? And this new process introduces expensive cost for the prover, and we are not even sure whether this cost can be optimized in the through other optimization techniques, for example, in the product galaxy. Right? Before, because this NARC actually it happens before our folding scheme. We need to first transform the NARC into ZK version, and then we execute this folding scheme. So we are not sure whether the cross term generated in this step can be optimized after the folding scheme. So we try to solve this problem in another way. So after review of the construction of our folding scheme, we have found a very inspiring observations. This observation is that actually our early stopping super Spartan, okay, is the encoding we execute and the 2 rounds of sum check we execute, right? This early stopping super Spartan, it already provides us a transformation technique, right? From a NARC to a ZK NARC. Why is that? Okay, so what is the NARC here? As I mentioned, the NARC is the CCS, right? Is the CCS relations. It's for the CCS relation. So after we execute the super Spartan protocol, what we have obtained? We obtained is an ACCS relations. Okay. So actually, we transform the old NARC for the CCS into a new NARC for the ACCS. And what's more, we have implemented zero knowledge for our folding scheme, the super Spartan, right? We have add some zero knowledge technique for it, and the ACCS we obtained is already zero knowledge. So the conclusion is that we do not need to introduce another new process for achieving the zero knowledge for the NARC. We can directly reuse our folding scheme to transform the NARC into ZK NARC. Okay, how do we do that? Okay, the conclusion repeated. We can obtain a zero knowledge NARC by utilizing our zero knowledge folding scheme. Okay, to achieve this, we can split the recursive circuit into two parts. Okay, remember the recursive circuit I have presented? Okay, it includes two sub-circuits. The first is the function f, the second is the verification for the folding scheme. So we do not integrate them together. We separated them. The first circuit include a function f, or a predicate anyway in the PCD. And the second circuit is for the folding verification. Then what we're going to do? What we do is that we first produce an instance witness pair of the first circuit. Okay, this circuit actually produce an instance witness pair in CCS. And then we take this CCS instance as an input for the folding scheme of the second circuit, right? We feed this CCS instance into the folding scheme verification. And by using the zero knowledge of the folding scheme, we can transform the CCS into a ZK ACCS. Right, a ZK NARC for ACCS. So before I introduce the concrete construction, let me give you the new theorem that we have developed. This theorem states that there is an efficient transformation that compiles any NARC with an efficient zero knowledge folding scheme into a zero knowledge PCD. Okay, we remove the requirements of a ZK NARC. We only have a zero knowledge folding scheme. Then we can compile any NARC into PCD. Okay. So this figure compares our new construction with the old construction given in IVC, in the Nova's IVC. So I have already illustrated the left figure just before, right? And for the right figure, we only need to notice 2 points. The first point is that we separate the recursive circuit into 2 parts. The part 1 only contains the function f, and the part 2 only contains the verification of folding scheme. Then the prover first executes the first circuit, the circuit 1 here, and the circuit 1 will output a CCS instance. This CCS instance is not zero knowledge, and we denote it as the U prime and W prime. Okay, and this U prime and W prime is then feed as the input of our folding scheme. Here we fold the U prime and W prime together into the ZK folding, the prover algorithm, and fold the instance, the public instance U prime, into the verification algorithm. And guaranteed by the zero knowledge of our folding scheme, the prover further writes the second circuit into a new ACCS, into a new CCS instance, right? And the folding scheme will fold our previous CCS into a folded ACCS. here, the ACCS. So since the folding scheme is zero knowledge, the output ACCS is zero knowledge. And where is the previous CCS? Where is this CCS? It actually is folded into the ACCS. So we do not need to worry about the witness is leaked from the instance we output, because we output a ZK ACCS. Okay. So this is our new construction for zero knowledge of IVC and PCD. Okay, so actually this new construction okay. This is the last point I want to introduce is the delegation part. Okay, I just quickly introduce my basic idea. So we have already obtained a ZK PCD, and it can support non-uniform circuits. But when we try to implement it, we have encountered some potential practical problems. Okay. The first problem is that if we keep fold, right, in the folding scheme, we need to fold the matrix. We need to fold MJ with another MJ prime, right? Then before the folding, the matrix may be some sparse matrix with only with only several positions of non-zero terms, right? But after we fold it with a linear combination, our folded matrix may not be dense, may not be sparse. It will be dense, right? So it prevents us from using some optimization technique such as the pre-processing, like the holographic setting, to optimize the cost for expressing this matrix, right? So each time we send the matrices, we cannot just send the non-zero terms. We need to send the whole matrices because it is dense. And also when we try to do some operations on the matrices, there will be a larger cost for the prover. And the second problem is that since we build PCD in a potentially multi-party system, and those parties are independent users. So from the user 1 to the user 2, if they try to carry out the computation, then the user 1 has to send the message, the necessary messages to the user 2. And in the message, there will be a large part of the matrices, right? Here is the node, the user A and the user B. Then the user A, after he has finished his computation, he has to send the instance to the user B. And this instance includes the circuits information, the matrices. Right. So sending the matrices will contribute to a large communication cost. Okay, so what we observed here is that the linear claims, the ACCS instance, right, that generated from our folding scheme, they only contains two claims. The first claim is about the matrix, and the second claim is about the vector Z. So in fact, those two claims can be checked independently. Okay. At the first glance, it seems a little bit doubtful, right? But after we actually do a security proof about this property, we have found that as long as we ensure that the challenge we used for the linear combination, the challenge C, for example, for the linear combination between different matrix and Z are the same, then we can independently check the matrix and check the claim on the vector Z. So, and another point is that those matrices, they are all public information, right? They are just represents the instruction set in the virtual machine and in other examples, right? So everyone in the network can access to this public information. So we can securely delegate the costly work of folding these matrices to a third party. Okay. Okay, so this is the idea, the main idea of our delegation. And based on this idea, we also develop a new construction for those delegation, right? And briefly speaking, what we only need to do is to keep that the challenge C we used for the fold of Z and the fold of M are the same, right? So with only this with this limitation, we can ensure that the whole system is secure, right? So we can safely run the original folding of Z, the computation in a PCD system, and we can delegate the costly folding of the matrices to a third party, and the third party only needs to run an IVC. Okay, the point is that by this technique, we can shift, right? We can shift the costly work to a more powerful third party. And what's more, since the third party here only runs an IVC, okay, he is an individual, an independent individual. He keeps track the computation in the PCD and folds the matrix correspondingly. And he does not need to send extra messages to other parties, right? Because here the IVC we do not consider the multi-party situations, right? And the third party do not to share those matrices to others. He just fold by himself. So this point actually eliminates the communication cost for the folding for the matrices. Okay, and all those advantages we believe will make our PCD system more practical. Okay. Okay, lastly, let me give you a brief summary. So in this paper, we actually proposed two cryptographic primitives. The first is an efficient generic folding scheme, and it supports non-uniform circuits and multifolding. And the second primitive is KiloNova, and it is a zero-knowledge non-uniform PCD. And we also contribute to a new theorem that it is actually an efficient construction for the ZK, IVC, and PCD. We remove a limitation that exists in the previous theorem. Okay, as for the future work, we try to first build a prototype for our zero knowledge PCD system, and we also try to find more applications. And a more long-term work is to further optimize or enhance the performance of our PCD constructions, right? And we actually we got some ideas for these optimizations. Okay, so that's all of my sharing. Okay, so thank you for your listening.
Thank you very much. Thank you very much,
Thank you.
Tianyu. I think we don't have much time for Q&A as we are over time quite a bit. But the presentation was
Sorry.
like really no worries about that. No worries about that. No worries at all. It was really nice. And the presentation and the explanations were really extensive and really deep. So I think everything was quite clear. I mainly wanted to say thank you very much for coming here today and going through the entire protocol and paper and explaining us in great detail all of these topics. And aside from that, I just wanted to basically thank you again. And in case you are okay with it, we will upload this talk to YouTube so that all of the people that missed it or wants to review some details or parts of the explanations can access it and review it again online if that's okay with you. How does
Okay.
this sound? Is it okay from your side?
Okay. Can you hear me?
Yeah, I can hear you. Is it okay from your side if we upload the presentation?
Yeah, sure.
Okay. Thank you very much, man. Thank you so much for coming here today and explaining all of this and talk to you soon.